Anybody not find them yet? Okay, make your little list. And you have them all and you have them written down, stand up. Olivia, how many do you have? She has 4. Okay, I'll add a number. Anybody else have 4? Anybody have more than 4? Anybody have less than 4? Okay. Abigail, what's the first one called? So you don't have them in order. You have them written down. Who has them in order? What do you got, Maria? This one is principal. And from now on, we're going to go principal to number, or quantum number, rather than rewriting it all. So put that in today's notes under today's date. We're going to make our little list, so we've got it to refer back to. Who else wrote them in order? Raymond, what's the second one? Yep, angular momentum. Quantum number. Okay, do you have number 3? Yep, good. Magnetic. Quantum number. And Abigail, what's the 4th one? I think you spoke to me first. Yeah. Spin. Quantum number. Okay. So those are the 4 things, like by the time you leave here today, those are the 4 things that you should understand what they are. We've got notes about them. Now we're going to kind of use those notes and put them all in a nutshell together and be able to identify them. These 4 things, ultimately, their job is to tell us where the electron is most likely to be in an atom. So they help us pinpoint the location of electrons, or at least predict very well where the electrons will be located. Now, before we get into all of those, there's something we have to establish. And I want you to think about this. I'm going to talk about hydrogen and helium versus all other atoms. So if I were to say hydrogen and helium, you guys should be able to tell me what their atomic numbers are, correct? What's the atomic number of hydrogen, Roy? 1. What's the atomic number of helium, Jaden? 2. So hydrogen has 1 electron, helium has 2, based on its atomic number. Both of these guys, both only want 2 electrons in their, oops, I got my email, in their outer energy level. We'll figure out why later on, but for now you just need to get that in your head. Hydrogen and helium only ever want 2 electrons. They don't want more than that. All the other atoms on the periodic table want 8 electrons in their outer most energy level. All the chemical bonding in the world, all the things we can make, it's all based on that. Getting the full outer shell. That's the whole job of an atom, or the whole goal of an atom, what makes them happy, to have a full outer shell. By using all these quantum numbers, we can figure out who does have a full outer shell, so they don't want to bond, and who doesn't, so we know they want to bond. Atoms wanting 8 electrons in the outer shell is called the octet rule, or noble gas configuration, and we'll find out why later on, or what this means really, noble gas configuration. So all the chemical reactions that take place are a result of this, the striving for 8 electrons. Alright, so, keeping that in mind, we're going to stop and we're going to talk about quantum numbers. So we're going to stop and we're going to simplify each type of quantum number. The first one you guys told me was principal quantum number. The principal quantum number tells me the number of the energy level, and it is represented by the letter n, the lowercase letter n. So if I see this, something like n equals 1, I know I'm talking about the first energy level. If I saw n equals 5, I would know we were talking about the 5th energy level, without writing everything out. When I talk about principal quantum number and I talk about energy levels, the lowest energy level equals the number 1, and it is closest to the nucleus. As I move farther out, away from the nucleus, like let's say my nucleus is here, as I move farther out, I could have n equal to 2 through 7. We usually don't go past 7. So the first energy level is closest to the nucleus, then the second, then the third, and so on until we get out to number 7. When I'm in the first energy level, I can only hold 2 electrons. These guys all want to get 8 electrons, 2 through 7. They all want at least 8. Some of them can hold more, but they want at least 8 to be happy. So what does principal quantum number tell me? What does it tell me? Gotta get it. Say it out loud. The energy level. We gotta get this in our brain, because if not, when it comes quiz time, it's not pretty. So principal quantum number tells me the energy level. The variable for principal quantum number is what letter? N. And it will have a value. N will be equal to what through what? 1 to 7. Don't forget the first energy level. All right, so that was my first quantum number. My second quantum number, what is it called? Good. Angular momentum. Angular momentum quantum number. And it tells the shape of the sublevels within an energy level. It's called angular momentum because it's based on the XYZ axis. It's 3D. In math, you pretty much just use X and Y. But when you're thinking in pictures, like we sometimes have to do in chemistry, you have to think 3D. So when you're in 3D, you have an X, Y, and a Z axis. So everything's angular. That's why it's called that. When I talk about the sublevels within an energy level, there are 4 types. So 4 different shapes. I can have an S sublevel, and that would be spherical in shape. It's a circle. A 3-dimensional circle, just like a basketball. Got an X, Y, and a Z axis. I have a P sublevel. And this one is called dumbbell shaped. And it's again on the X, the Y, and the Z axis. So I have one that runs this way, one that runs this way, and one that runs that way. And they're all stacked on top of each other. So there's a lot of different paths an electron can follow. The F sublevel is called four-leaf clover shape. I'm just going to draw one of them, and then I'm going to show you a real picture. Okay, just to be easy. Change that. I chose the wrong letter. Everything else is right. This should be D, not F. I'm ahead of myself. What do you think the last one is? F, good. Can I move this? All right. So F, and all we're going to say about F is it has a complex shape. Okay? You can grab it in whatever order. Yeah, it's from all the different parts. Yeah. All right, so it's super complex. I thought I had. Oh yeah. Okay, so let's look at this piece. It's much better than my bad drawing. So this would be S, just the sphere. And then P, we have the three different positions. And then when we get to D, it gets even more complex. They're all kind of clover shaped. And then when we get to F, we're looking at the green and the blue. All of those different little blobs represent like different paths an electron could follow within that particular sublevel, within that energy level. So it gets complex, it gets a little confusing, and we're not going to try to draw them. But we are going to understand this. If I have an atom that goes to, say, the fourth energy level, this is what starts to happen. I have my first energy level, then I have my second, which will hold my P, and then if my D is involved, I start getting something that looks like this, and then if my F is involved, I start getting even more jumbled up. There's a reason, or there's a name that we call this now that they didn't used to call it because they couldn't see it and they didn't understand it. This is called an electron cloud. So we talk about energy levels, but if we're talking about all the electrons within an atom and their positions, it's called an electron cloud. Am I going to ask you to draw this? Absolutely not. Am I going to ask you to know what this word means? Yes. Could I ask you, why does it look like a cloud? Yeah, because they're all overlapped over each other. And it's hard to read and it's hard to see. All right. So let's move to our next quantum number. Ooh. What's number 3? Good. Magnetic quantum number. Magnetic quantum number. And it's, let's see, it tells us about the sublevels and the number of electrons each sublevel holds. I'm going to make a little chart. Okay. So I'm just going to make a little chart. I'm going to put S, P, D, and F. So those are my sublevels. I'm going to talk about how many positions they have to hold electrons. A position is just a line. That's how we show it. And each position or each one of these lines you see can hold possibly 2 electrons. Not anymore. Maybe only 1. But it can hold 2 if it's full. When I talk about the S sublevel, it has 1 position. And that would be shown as just 1 line. If it has just 1 position, and each position can hold 2 electrons, what's the maximum number of electrons that can be in S? Ava? Just 2. So its maximum would be 2 electrons. When I move to P, I find there are 3 positions, which would mean there are 3 lines that can hold electrons. If I have 3 lines and each line can hold 2, my maximum will be 6 electrons. When I move to D, there are 5 possible positions, so I would show 1, 2, 3, 4, 5 lines. How many total electrons could be held? 10, yeah. So there's a multiplication problem. And then finally, F has 7 positions, so it can hold 14 electrons. So now I know energy level goes with principal quantum number. S, P, D, and F go with angular momentum quantum number. And the number of positions within a sublevel go with my magnetic quantum number. I have one quantum number left. What is it? Oh, what is it? Yeah. Spin quantum number. And this tells the way the electron is spinning and moving in its sublevel within its energy level. There are two values. Two values for spin. There's a plus 1/2 and there's a minus 1/2. Plus 1/2 I show like this, like half of an arrow. Minus 1/2 is a half of a downward shaping arrow, pointing arrow. If I have a pair of electrons within a sublevel, they spin in opposite directions. I have a pair of electrons within a sublevel, within a position, they spin in opposite directions. So I would have my position shown. If it has two electrons within it, I would have one electron that moves in the positive 1/2 and one electron that's moving in the negative 1/2. I'm going to let you write that, and then I have a question I want you to think about. See if you can answer it. So if I have two electrons within the same sublevel, within the same position, why would they spin in opposite directions? What's the charge on an electron? Negative. If I have two negatives next to each other, what do they want to do? Get away from each other, right? So one spins this way and the other one spins the opposite because they're repelling each other. They don't like being together. So keep that in mind. That's why we never have two ups or two downs. All right, now, let's think about all of this information and put some of it together. So my principal quantum numbers would be 1. I'm just going to use through 7. So that's my principal quantum number, and that represents the energy level. Within the energy level, I have what? What are S, P, D, and F called? I know they're angular quantum numbers, but what are they called? What do they represent? What? Sublevels. So now we're going to look at who has what sublevels. When I'm in the first energy level, I only have an S sublevel. Everybody else has an S2. Or also, I should say. So the first energy level only has one sublevel. That sublevel is S. So how many? Oh, I'll see that later. All right. When I move to the second, I now have a P sublevel. And I would really write that 2S, 2P. That's how I would show that. Nothing more. Everybody else also has a P sublevel. When I move to my third energy level, I add another sublevel. SP, what comes after P? P. So I have a 3D here. And so on, all the way down. I move up an energy level. I add my last sublevel, which is what? So in my first energy level, which is my principal quantum number, I only have the S sublevel. S sublevel has how many positions? S, 1. And it can hold, that position can hold how many electrons? 2. So in my first energy level total, I will only ever have 2 electrons. Hydrogen and helium. When they're out of energy level 4, it's the first energy level. It can only hold 2 electrons. Now, figure out how many electrons each of the rest of these can hold. Use what we did today and see if you can figure that out. You have enough information to figure it out if you use your notes. Raise your hand if you think you know how to do this. Only 2 of you think you know how to do it? Yeah, maybe. Roy, tell me what you're doing. Okay, so I would have 2 electrons here. What'd you do with this? Okay. So then all I do is add it together. So this can hold a total of 8 electrons. I would do the same thing here. S can hold 2, P can hold 6, D can hold how many? 10. So what is that? 18 electrons. Same thing here. S holds 2, P holds 6, D holds 10. F holds how many? 14. And when I add that up, it equals 32 electrons. All the way down. So I want you to get out an index card. And if you don't have one, go back to the drawer and get one. The last thing I want you to do today, I want you to create an index card, and I want you to put your name on it, and I want you to title it Order of Filling, and then I just want you to copy this with the arrows in the right places, because we're going to use it tomorrow.